Welcome back to Calculus 1. I'm Dr. Jeff Groh, and today we're going to talk about functions and their inverses. As you know, every relation has points x and y, and every relation has an inverse relation obtained by reversing those coordinates. The idea being that if you're a relation, you take an x and associate it by that relation with some y. The inverse relation goes in the opposite direction. You'll recall a relation is a function if it satisfies the vertical line test. The inverse relation always exists, but if the inverse relation is not a function, it won't satisfy that vertical line test. How do you know when a function will not have an inverse function? And the answer is, a function has an inverse function if and only if it is one-to-one. If and only if you can't find two different x values that have the same y value. So a function that has two different x values and the same y value is not one-to-one. Its inverse relation is not a function. A function will have an inverse function if and only if it is one-to-one. If a function has an inverse function, that inverse is unique. If the function is denoted by f, its inverse is denoted by f with a superscript of -1. Now, when we write f with a superscript of -1, we specifically do not mean the reciprocal. We mean inverse function. If the function f takes some x and outputs some y, then the inverse function does the opposite, takes that y and sends it back to the original x, which means that definition of inverse function, we want f inverse of f of x to be x. Whatever f does to the x, f inverse undoes and sends it right back. F of f inverse of x will also be x. Whatever f inverse does, f undoes. Inverse functions behave according to these two properties. By definition, if you have a function f of x, which is b to the power of x, its inverse is, by definition, log base b of x. This means the following two properties hold. If I take log base b of b to the power of x, I get x, and b to the power of log base b of x is x. So these things cancel each other out in this fashion. We already have the following two facts. What I want to know next is, how do I calculate the derivative of an exponential function having any other base? And how do I calculate the derivative of a logarithm to any other base besides the natural base, e? So, let's start with y equals b to the power of x. How then do we calculate the derivative? What we can do is we can play a little game, an algebraic game, and convert this into something that we already know how to do. The trick is to take e to the natural log of b to the x. Because e to the power of and natural log are inverse functions, this would cancel and give us b to the x, so we know it's equal to what we started with. But we can use the property of logs to bring this x out. And with x times the constant, the natural log of b. We already know that if we take the derivative of e to the power of ax, you get a times e to the power of ax by the chain rule. In this case, then, we'll get the natural log of b times e to the power of x times the natural log of b. The natural log of b being a constant. However, e to the x natural log of b is equal to the original function. So we get the natural log of b times b to the power of x. When you take the derivative of b to the power x, you don't get b to the power x. You get b to the power of x times the natural log of the base b. I'm going to codify what we just did as a formula that you need to remember. The derivative of b to the power x is the natural log of b times b to the power of x. And you need to memorize this. As an example, if y is equal to 2 to the power of x, then y prime is the natural log of 2 times 2 to the power of x. If y is 10 to the power of x, then y prime is the natural log of 10 times 10 to the power of x. Sometimes, if you know how long it takes for a population to double, the doubling time, you can make special use of the following formula. If t sub 2 is the doubling time, then the population size should be equal to the initial population size times 2 to the power of t divided by that doubling time. So for example, if the doubling time, say for a particular bacteria, is say 6 hours, and the initial size is 109, then find p when t is equal to, say, 24 hours. The answer is 109 times 2 to the power of 24 divided by 6. 6 goes into 24 4 times. 2 to the power of 4 is 16. So we have 109 times 16. My calculator tells me that's 1,744. On the next part of the problem, I want to find the rate of change of the population with respect to time. P naught is a constant, so I get P naught times the derivative of 2 to the power of t divided by t2. The derivative of 2 to the power of is the natural log of 2 times 2 to the power of t divided by t2, but we need to multiply by the derivative of the inside, and that's 1 divided by t2, because the derivative of t is just 1. So the rate of change of population will be the initial population size times the natural log of 2 times 1 over t2 times 2 to the power of t over t2. So we now know how to calculate the derivative of any exponential function, no matter what the base. What I want to do next is calculate the derivative of any logarithm, regardless of the base. I'll convert this into a problem we know how to do. we'll take b to the power of both sides of this equation. The log base b and the b to the power of function cancel, leaving me with simply x on the right-hand side. We know how to take the derivative on the left-hand side, but you need to remember y is a function of x. So we have a function of x inside of some other function, a function composition. That means we need to apply the chain rule. If we apply the chain rule to the left-hand side, the derivative of b to the power of is the natural log of b times b to the power of. But then, by the chain rule, we need to multiply by the derivative of the inside function, and that's y prime. On the right-hand side, the derivative is mere 1. We obtain then that y prime is 1 divided by natural log of b times b to the y, but b to the y is x. We proved then that the derivative of log base b of x is always not 1 over x, but 1 over the natural log of the base times x. And that's a formula I want you to memorize. So for example, if I have y equals log base 2 of x, then y prime is 1 over the natural log of 2 times x. If I write y equals log of x, normally at this level, when we write log, we mean log base 10. In that case, y prime is going to be the natural log of 10 all times x. So I have some tricky ones for you. Suppose that y is e to the power x. You know that y prime is e to the power x. But if y is x to the power e, what is y prime now? Now you have to use the power rule. Bring the power down and then subtract 1 from the exponent. So if I have y equals pi to the x, y prime is the natural log of pi times pi to the x. But if I have y equals x to the power pi, y prime is pi x to the power pi minus 1. Now, where things get a little complicated is if I have y equals x to the power of x, which is neither a power function nor an exponential function. How do I take the derivative of x to the power of x? I need to get this x out of the exponent. The way to do that is to use logs. So I'll take the natural log on both sides and use logarithmic differentiation. This little x can come out front, giving me x times the natural log of x. To take the derivative on the right-hand side requires the product rule. The derivative on the left-hand side requires the chain rule. On the left-hand side, the derivative of log is 1 over, leave the inside alone, and then multiply by the derivative of the inside. And that's y prime. On the right-hand side, we use the product rule. Derivative of the first times the second plus the first times the derivative of the second. Multiplying by y prime is going to be natural log of x plus 1 all times y, and that is x to the power of x. Okay, so since you're so smart, how do you calculate the derivative of x to the power of sine of x? Same trick. Take the natural log on both sides. Using the property of logs, we'll get the sine of x times the natural log of x when we bring the sine out front. Then we'll have a product rule and a chain rule. 1 over y prime is derivative of sine is cosine times the second plus the first, sine of x, times the derivative of the second. And no, you may not cancel the x's here. The first x is inside of the sine function. It's doing horrible things to it. You don't even want to know. Not until calculus 2. We multiply both sides by y in order to solve for y prime. So we'll have cosine of x, natural log of x, plus sine of x over x, all times y. But y is x to the power of sine x, and that is how you calculate the derivative of x to the power of sine x. So how do I calculate the derivative of y equals log base 5 of x plus 1? Well, the derivative of log base 5 is 1 over the natural log of 5 times the inside stuff. But by the chain rule, you have to multiply by the derivative of the inside. And so, there it is. In our next example, we'll calculate the derivative of y equals x times the log base 3 of x. We clearly have a product rule on the right-hand side. Derivative of the first times the second plus the first times the derivative of the second. Derivative of log base 3 is 1 over the natural log of 3 times x. This x cancels, and so the derivative is log base 3 of x plus 1 over the natural log of 3. I want you to see something. Suppose I have y equals the natural log of 2x. The chain rule says the derivative of log is 1 over. Leave the inside alone. But then you have to multiply by the derivative of the inside. And that leaves you with 1 over x. That's the derivative of the natural log without the 2. Why does this function have the same derivative as the other? The answer comes from properties of logs. ln of 2x is the ln of 2 plus the ln of x. Logs turn products into sums, but ln of 2 is constant. So the derivative of the first term is 0. The derivative of the second term is 1 over x. Remember that a function has an inverse if and only if it is 1 to 1. A function is 1 to 1 if and only if it satisfies the horizontal line test. So for instance, let's look at the sine function. The sine function is not 1 to 1. It fails the horizontal line test badly. So it has no inverse function. So what explains the inverse sine function on your calculator? The answer is, we want there to be an inverse so badly that we're willing to stand on our ears and make it have an inverse, but only on a restricted domain where it is 1 to 1. The largest interval where the sine function is 1 to 1 goes from minus pi over 2 to pi over 2. So if we restrict the sine function to minus pi over 2 to pi over 2, it will output numbers between -1 and 1. And on this restricted domain, there will be an inverse function. That inverse function will map the interval from -1 to 1 into negative pi over 2 to pi over 2. So the inverse sine function only outputs angles in quadrants 1 and 4, and only in quadrant 4 between negative pi over 2 and 0. We have then that the inverse sine of the sine of x is x, but only if x lies within our restricted domain. Other values of x will not give you x. It'll give you something else. If the graph of the sine function on the restricted domain is like this, then the graph of the inverse sine function is like this. Note that the inverse sine does not have vertical asymptotes. It terminates at this point at pi over 2, and this point, negative pi over 2 on the y. What we'd like to do next, calculate the derivative of the inverse sine function. To do that, let's set y equal to the inverse sine of x. We want to find y prime, but we don't know how to calculate the derivative of inverse sine yet. We do know how to calculate the derivative of sine. So we'll take the sine on both sides. A function and inverse function cancel each other out, leaving us with merely x on the right-hand side. When we take the derivative on the left-hand side, we need to be careful to use the chain rule because we have a function of x inside of a function. So taking the derivative on the left-hand side implicitly, we get cosine of y times y prime. That's equal to 1. It follows then that y prime, the thing that we were looking for, is 1 over the cosine of y. Still not content, keep in mind that the inverse sine function looks like this. It has a slope that's positive everywhere. I can rewrite this as y prime equals 1 over the positive square root of 1 minus sine squared y using the Pythagorean identity. Positive because the slope is always positive for the inverse sine function. But we know what sine of y is. Sine of y is x. So I can rewrite this as 1 over the square root of 1 minus x squared. We have then the following hard-won fact. The derivative of the inverse sine of x is 1 over the square root of 1 minus x squared. You are going to memorize this. Okay, now that you know how to calculate the derivative of inverse sine, how about inverse tangent? It's the same idea. Take the tangent on both sides. The tangent of the inverse tangent cancels, leaving you with x. The derivative on the left-hand side is secant squared of y times y prime. On the right-hand side, the derivative is 1. It follows that the derivative that we seek is 1 over secant squared of y. But now you need to remember one of the Pythagorean identities. You probably remember that cosine squared x plus sine squared x is equal to 1. If you divide everything in sight by cosine squared x, you'll get 1 plus tangent squared x equals secant squared x. So y prime is 1 over 1 plus tangent squared of y. But remember, tangent of y is x. So we get 1 over 1 plus x squared. We have then the derivative of the inverse tangent of x is 1 over 1 plus x squared. You're now wedded to this. This is the one. Whenever I tell you that's the one, that's what you're going to think of. I make you remember these things in a silly and stupid way because that way, if you forget something during the exam, I could just mention to you, oh, that's the one. And maybe then it will jog your memory and you'll remember it. But that's the one. You're wedded to that forever now. That's it. And there's the other one. The derivative of arcsine is 1 over the square root of 1 minus x squared. You need to know both of these. You might be wondering about cosine. Suppose y is the inverse cosine of x. Then the cosine of y is equal to x, but do you remember the cofunction identities? The cosine of theta is the sine of pi over 2 minus theta. So the cosine of y is equal to the sine of pi over 2 minus y. Now, let's figure out how to do the derivative. On the left-hand side, we'll have the cosine of pi over 2 minus y times negative y prime when we take the derivative of the inside. We have to use the chain rule. On the right-hand side, we have 1. And by another cofunction identity, this is the sine of y. It follows then that y prime is minus 1 over the sine of y. And what is more, the inverse cosine function looks like this, which means the slope is always negative. It's like drawing the cosine curve around the y-axis, but stopping before it ceases to be a function. So we're going to have negative 1 over the square root of 1 minus cosine squared of y. Using the positive square root and the negative sign ensures that the slope be negative. And this gives us negative 1 over the square root of 1 minus x squared, since cosine y is x. This is just the negative of the derivative of inverse sine. We have then that the derivative of arc cosine is minus 1 over the square root of 1 minus x squared. Notice it differs from the derivative of inverse sine just by a minus 1. The derivative of a co-trig function, like cosine, cotangent, cosecant, is the negative of the derivative of the non-co function, sine, tangent, secant, and for the same reason, because of the cofunction identities. We really only need to prove one more, and that is for secant. If we get secant, we'll automatically have cosecant because it's just minus. We have tangent, so cotangent will be minus 1 over 1 plus x squared because it's just minus the derivative of inverse tangent. So the last example that we need to derive is for y equals inverse secant of x. You can see then that taking the secant of both sides gives us secant of y equals x. The derivative of secant is secant tangent, but by the chain rule, we have to multiply by the derivative of the inside, which is y prime. Solving for y prime, we have 1 over secant of y tangent of y. We know secant of y is x. All we have to do is get rid of this pesky tangent. This is going to be a little tricky. We need to know a little bit about what the function inverse secant looks like. It's the inverse of the secant function. Remember what the secant function looks like? Cosine is like this. Where it crosses through the axis, we'll put in a vertical asymptote. The secant function looks like this. In order to have an inverse, we need to restrict the domain to a region where it is 1-to-1. The inverse secant, then, will look like the reflection through the line y equals x. We'll have a horizontal asymptote at pi over 2. This is at the rate of 1. We'll have a 1 here, and the curve will tend towards that horizontal asymptote on this side. It tends towards the same horizontal asymptote coming down from pi on the other side, sitting at -1. Let me draw that again so you can see that perhaps more clearly. Note something about this. This is the graph of inverse secant. The slopes are always positive wherever they exist. That's the salient fact I needed to point out from the graph. The slopes are always positive. Now, remember that 1 plus tangent squared theta is secant squared theta. We can move the 1 over and then take a square root to the tangent. Tangent theta will be plus or minus the square root of secant squared theta minus 1. So what we have here is that y prime is 1 over x times plus or minus the square root of secant squared of y minus 1, but secant of y was x. So we have 1 over plus or minus x times the square root of x squared minus 1. Now I need to be careful. This was always supposed to be positive. This will only exist when x is bigger than 1 in magnitude. So we need x bigger than 1, not equal to 1, in order to get this derivative to exist. But when x is positive, we need to make sure that we use the plus. When x is negative, we need to use the minus. That gives us the following. Absolute value of x, square root of x squared minus 1. That's the derivative of arc secant. We have the derivative of arc secant is 1 over the absolute value of x times the square root of x squared minus 1. And of course we require that the x values have a magnitude greater than 1, or else we get a negative under the square root, and hence imagined values. The derivative of cosecant inverse would just be the negative of this then. Okay, so I'm only going to require that you remember two of these, the one and the other one. There is a slightly general theory. Let's play this game one more time. But more generally, let's suppose that we have some inverse function, f inverse. If we calculate the function f, we apply that to both sides, then on the right-hand side we just get x. Using the chain rule, the derivative of the left-hand side is f prime of y times y prime. The derivative on the right is just 1. Therefore, y prime is 1 over f prime of y, but remember y was f inverse. So it's 1 over f prime of f inverse of x. That's the general principle. In general, we have the following theorem. The derivative of f inverse of x is 1 over f prime evaluated at f inverse of x. We could have used this to derive all of those formulas that we just found. In our next example, we're going to suppose f of x equals the square root of x plus x cubed. Now, this function has an inverse function. And note that f of 1 is equal to 2, so that f inverse of 2 equals 1. I want to find the slope of the tangent line to f inverse of x at the point 2, 1, which lies on the graph of the inverse, not the function. The point 1, 2 lies on the graph of the function, so the point 2, 1 lies on the graph of the inverse. In our solution, we need to calculate the derivative of the inverse, which by our formula was 1 over f prime evaluated at f inverse. If this is some number a, we can put number a over here. We'll plug in the number 2. First, note that f prime of x is 1 over 2 root x plus 3x squared. We have then the derivative of f inverse at 2 is 1 over f prime evaluated at f inverse of 2, which we know to be 1. Now, recall that f prime of x was 1 over 2 root x plus 3x squared, which means we have 1 over 1/2 plus 3. 3 is 6/2 plus 1/2 is 7/2. The reciprocal of that is 2/7. I want you to consider the following function. Arc cosine of x plus arc sine of x. Check this out. The derivative of arc sine is the other one that I asked you to remember. But the derivative of the cofunction is merely the negative of that. The derivative is 0 everywhere. We will show that if a function has a derivative equal to 0 everywhere, that implies the function is constant. But the original function was inverse cosine plus inverse sine. What is this constant? We can evaluate at one point and find out. Let's evaluate at 0. Now, since sine of 0 is 0, inverse sine of 0 is also 0, because inverse functions simply swap x and y coordinates. So what is the inverse cosine of 0? It's the angle you plug into cosine that outputs 0. That's pi over 2. So the constant is in fact pi over 2. We've just proved an interesting identity. We have inverse cosine of x plus sine of x is pi over 2 for all x between -1 and 1, where these functions are defined.